Thank you very much for having me. It's a real pleasure being here. My thesis work is on a task called statutory reasoning, and I do this in the context of US tax law. However, despite this, my talk won't contain any advice on how to minimize your taxes. So if you read the announcement email and thought perhaps this is it, we're getting free financial advice, I'm really sorry to disappoint you, but don't leave, please don't leave. I promise it's actually worth your time. Next. This isn't working. Okay, good. Do I have a pointer? Yeah. Okay, so I recently looked at Best Paper Awards at NAACL this year, and I think that's an interesting thing to do because it tells us what the community thinks are important topics in NLP. So what tasks does the community think are exciting tasks in NLP? And so one thing I can tell you is that people are excited about few-shot learning. So 3 out of the 6 Best Paper Awards were about few-shot learning. And so in that context, it's about can you learn a new NLP task using 1, 2, 3, or up to 100 examples. And the way to do this is to look at some form of natural language description of the task, and then feed it to the model and expect the model to understand the description, and then go and do the task. Where does the description come from? So there are typically 2 cases. Usually it comes from an annotation manual. So it's some human who wrote a description of the task for other humans to read and produce samples of the task. Another possibility is that the researchers just wrote ad hoc descriptions for the problem of few-shot learning. So in both cases, it's somewhat artificial. There's no task that actually comes equipped with its own natural language description. So when I saw that, I realized that actually the task I'm working on actually perfectly fits that framework. So it's a task that requires few-shot learning. It's a defining feature of the task. But contrary to those NAACL papers, the task actually comes equipped with descriptions. In fact, the descriptions are the key to being able to do the task. So when I realized that, I congratulated myself, gave myself the Best Paper Award. And so here's what statutory reasoning is in a few sentences. So if I had to summarize it at a high level, it's about predicting how laws apply to legal cases. That's something that legal professionals have to do all the time. Whenever they're considering a new case, they have to quickly figure out which laws, which regulations apply. That's not all they do. They have to look at a ton of other things. One of them is precedent, but that's just one of them. So it's strictly a subset of what you could call legal reasoning. It's a task that requires natural language understanding. You have to understand the laws that you're looking at. You have to understand the cases, and most of that is described in natural language. But then you also have to do something you have to do a very rigorous form of logical reasoning. So you need both of these abilities. It's a fundamental task for legal NLP. I'm just going to give 2 reasons. The first one is that you could use statutory reasoning to predict how new laws are going to interact with past cases, or even with hypothetical cases. So the goal here is before you even publish a new law, you might be able to test it on past cases or test it on imaginary situations which help you understand. Another way that statutory reasoning is important is that it's a required step if you want to model the logic behind legal rules and the logic behind logical argumentation. So if you imagine this as a large system of rules that sort of depend on one another, and it's a complex logical system, then if you want to find loopholes or problems with that system, then probably you would need to be able to do some form of statutory reasoning. So lawyers tend to specialize to specific domains because the law is simply a very complex body which deals with different topics. And so I decided to work specifically on US tax law. So the types of cases I'm interested in look somewhat like this. So they contain a number of facts stated in natural language. So typically, Alice made this much money in 2017. Alice is married. Alice has this many children. And then the types of questions that I'm interested in answering about this specific paragraph are things like, how much tax does Alice have to pay in 2017? So that's a broad question. And there are more specific questions like, does section 63 F1A of the tax code apply to Alice in 2017? So the way to answer this is to look at all of tax law. And for our purposes, that's a collection of documents which contain rules expressed in natural language. So how do you do this? So since NLP is increasingly an applied machine learning problem, you would simply collect a large corpus of cases, a large corpus of laws, and then you would ask humans to tell you which rules apply to which cases and which rules don't apply to which cases and so on, and to draw any conclusions from there. So that's actually very unrealistic for statutory reasoning and for the following reason. So everyone has to pay taxes every year, and in particular, companies have to pay taxes every year. And companies that are large enough, they can actually afford to hire an army of lawyers and accountants and to tell them, we have to pay taxes, it's a necessity, but we want to make sure we pay the smallest possible amount. And so those lawyers and accountants, they pore over the entirety of the tax law corpus. So I'm exaggerating a bit, but that's the idea. They look at all of tax law, they look at the company's activities, and then they decide, we're going to frame the company's activities in the following way, and we're going to interpret the statute in this way. And the result that they come up with, they file in a tax return. And then that tax return is examined by some authority. So in the US, it's the Internal Revenue Service, so the IRS for short. Most of the time, the IRS will approve the return, but in a tiny fraction of cases, they will actually look at the return more closely. And sometimes they will find that the way that the company has interpreted tax law, that they disagree with that. And so perhaps they'll say, well, we disagree with this part and we need more information about this other part. So they might ask the company to do an adjustment. And so as part of that, the company might have to produce more evidence about what they do, about their activities. And then there's a back and forth with the IRS. As a result of this process, the company and the IRS are going to come to some form of agreement as a settlement, where the company says, okay, I'll pay this much money to you, and we just don't go to court. And so those documents are very, very interesting for us researchers in legal NLP, because they contain a lot of information about what the company has done and how tax law applies to those activities. But that information is actually kept secret because it contains a lot of information about the company's activities, and the company just doesn't want its competitors to know about that. So that's usually completely secret. As a result of that process, the lawmaker, so that's Congress in the US, together with the IRS, they might issue new laws and new regulations based on what they've learned by interacting with this company, or perhaps to clarify certain points in tax law, or to simply prevent certain types of behavior. And that is added to the vast corpus of already existing tax law. Okay, so to summarize this, we don't have many publicly settled cases. In fact, almost zero. And new laws and new regulations are added frequently. So that's either based on the kinds of loopholes that were discovered based on tax returns, or just independently. The economy changes all the time. Congress has to keep up. Congress has to keep up with it, so they keep passing new laws. So the result is a sparse data setting with very few pairs of laws and cases where you positively know whether the law applies. So because of that, you essentially have to do few-shot learning. That's just part of the problem. And in that context, you can think of laws and regulations as their own task descriptions. So what's interesting about laws is that they actually tell you how to know whether or not they apply. So as in regular machine learning, you need to be able to learn from cases in the training set and then to generalize to cases that you have never seen before. But you also need to learn from rules themselves. So you need to learn from the semantics of rules, understand why they apply, in order to be able to predict for new rules and new laws whether or not they're going to apply. Okay. Why is tax law so interesting? So for AI in general and for legal NLP, I think tax law is a really good area to work on. I'm going to give two reasons. So the first one is that absolutely everyone has to pay taxes, or rather everyone has to file taxes. So even if you don't pay taxes, you still have to file them. So any any advance, any application in that area has a really large impact. The other reason is that if you think about how cases go in tax law, the main the main outcome of a case is an integer number, which represents the amount of tax that is owed by someone. So that kind of contrasts with other domains in law where the outcome is not necessarily so clear-cut. So it's not just about who wins the case, there's a bit more to the story. So in that respect, cases in tax law are a bit more measurable. Okay, so this is a task that's interesting in legal NLP, but statutory reasoning is also interesting to the wider domain of AI and NLP. The key part here is that you have to do reasoning with rules specified in natural language. And the interesting thing about legal rules is that they are true because they're agreed to. So they're typically stated once or a couple of times at most, and you can assume that they will always be true. So that contrasts with rules that you can infer from evidence. So for example, if you pour out a large corpus of text, you might be able to infer rules of grammar or of syntax. And then statutory reasoning is interesting because it combines, so on the one hand, natural language understanding, and then on the other hand, rigorous logical reasoning. So bringing these two together is one of the goals that AI has been going after. Okay, so I'm a PhD student at Johns Hopkins. I'm in my 5th year, and my advisor is Ben van Dermy. And Ben is also an advisor to Andrew Blair-Stanek. And Andrew happens to be, so he's a PhD student with us, but he is also a full professor for tax law at the University of Maryland. So this thread of research I'm going to talk about was done in very close collaboration with Andrew, and obviously with Ben as well. So I'll present two things. The first one is a dataset that we built for the purposes of statutory reasoning. And then the second project was about just making progress on that task. Okay. So to be able to measure the ability of some model to do statutory reasoning, we started by simply building a dataset to measure performance. And so we published that at the Natural Legal Language Processing workshop last year. So I'm going to highlight the most interesting aspects of this paper. But if you're interested in hearing more about this, I was invited to the NLP Highlights podcast. And so in that episode, I discuss lots of details about this paper and also a little bit beyond. Okay, so I mentioned that statutes, like laws in general, tax law statutes are a collection of documents. And each document is a section of the statutes. And it centers around a specific topic. And then it refers to other sections because concepts build on top of one another. And so they depend on one another. So the first step was to pick a subset of that would be self-contained. And so that's what we started with. We picked 9 sections from tax law that center around income tax and employment tax. And then we pruned them so that they would form a self-contained graph of rules. These sections subdivide into subsections, paragraphs, subparagraphs, clauses, subclauses, down to individual rules. So for each of these individual rules, we wrote 2 test cases, one where the rule applies, one where it doesn't apply. And then in addition, we had a number of cases where the goal is simply to compute the amount of tax owed. So crucially, Andrew, who's a tax law professor, checked each case, as well as the interpretation of the statutes. So we were careful to retain as many features of tax law as possible, so that despite being a synthetic problem, we still sort of retained most of its properties. And so I'm going to walk through them now. So assume you just wanted to compute the amount of tax that you owed under this data set. Here's how it would go. And also, I forgot to mention, but I'll be referring to this data set as SARA throughout the rest of this talk. It stands for Statutory Reasoning Assessment. Okay, so how much tax do I owe? So you would probably start by pulling up section 1, which is just the regular tax schedule. Please don't read it. It's really long and complex. But the first thing to notice just visually is that statutes have a hierarchical structure. So there's a there is a section, subsection, paragraph, subparagraph. And that hierarchy between rules is actually, it's materialized, and it's in the format of the text itself. It has plenty of indents everywhere. I didn't add those. They were there already. So we are talking about tax law. So there is a lot of numerical reasoning. And in particular, there are lots of formulas that are expressed in natural language. I mentioned that statutes depend on one another. So here are some examples of this. So here's an explicit reference to another section. That's a pointer to section 2A. And then sometimes these references are implicit. So for example, the words taxable income here, they are an implicit reference to a concept that's further defined in section 63. So let's say you looked up section 2A. You would find that to interpret section 2A, you need to know what a son, stepson, and daughter or stepdaughter are. So those terms are not further explained anywhere in the statutes. And so these kinds of things you would have to know as part of a form of common sense knowledge. Taxes are paid every year, so you need to be able to figure out what happened relative to a given taxable year. What events happened before, during that year, or after. Lots of sections actually define terms or concepts. So typically, those definitions will be built around a general case. So in all the following cases, this general rule applies. And then it's usually followed by a number of exceptions. And so anytime an exception is triggered, you would have to go and reinterpret the general rule. And then finally, there's a small number of conditional counterfactuals. It's hard to explain what conditional counterfactuals really are, but this is one of them. So it would be worth working on each of these features specifically. Each of them you could build dedicated subsolvers for. And on top of that, I'd like to point out that lawyers and legal scholars can argue about individual words in statutes. And there are about 10 times more interpretations and guidelines than there are actual statutes. So every time Congress passes a new law, the IRS has to write guidelines and regulations that explain what those statutes mean and how to apply them in practice. So all of this is to say that tax law statutes are a lot more dense than the language that NLP usually has to deal with. Okay, so we designed this data set to require both natural language understanding and logical reasoning. And to prove that it's sufficient to solve this task, we wrote a prologue solver. So that was made up of two parts. The first one was a translation of the statutes to a set of prologue predicates. And the other part was a translation of the facts in each case to a knowledge graph. Okay. So to translate statutes, we framed each rule, so that's a subsection or a paragraph or a subparagraph, we framed each of those as a predicate, which takes as argument a case and which can be true if the rule applies and false otherwise. So each subsection here becomes the head of a horn clause. And then the body of the horn clause is simply an interpretation of the semantics of the statutes. And then to translate the facts in a case, we had to rely on an ontology of events. And so we picked an ontology that was roughly at the same level of granularity as the statutes. So anything that the statutes don't further define, we assumed was an atomic event. And so the result is that we can translate a sentence like that with this very interpretable representation. So at this point, we have a prologue program, which faithfully represents the semantics of the statutes. And then we have knowledge graphs, which faithfully represents the facts represented in each case. And with that, we're able to perfectly solve the statutory reasoning task on the SARA dataset. So at this point, you could stop and just say, that's it, we've solved statutory reasoning. All we need to do is write prologue code. So that's an interesting idea, and it has been pursued in the past, but it has a number of limitations. So one of them is that new laws and new cases are being added frequently, so you would have to write prologue code all the time. And that's actually not simple, regular prologue code, because you need, on the one hand, lawyers or legal professionals who can understand the statutes and interpret them, and tell you how they're to be applied. And on the other hand, you need computer scientists to write functional Prolog code. You could also try to produce the Prolog code automatically. So it turns out that automatic semantic parsing isn't good enough for that task yet. And another problem could be that if you even have a tiny mistake somewhere, all your conclusions could be wrong, or the program could simply not run. So since we store laws in the form of natural language to begin with, and since all the cases are mostly documented in language, not only, but it's mostly in language form, it would be interesting to figure out whether machine reading can do this task for us. And so for that, we recast statutory reasoning into a number of just regular machine reading tasks. So for cases where the goal is to predict whether a given subsection applies or doesn't apply, we recast this as recognizing textual entailment. And then a case where the goal is to predict the amount of tax owed, we recast this as a regression problem. So to get an idea of how useful the prediction of the model is, we didn't use regular metrics like mean squared error. Instead, we devised a form of accuracy based on substantial understatement of tax. So essentially, the idea is that if your answer is within a certain range of the correct answer, then we just say that your answer is fine. It's correct enough. And then that range just depends on the absolute value of the answer, of the goal answer. Okay. We tried a number of baselines built around BERT and built around word vectors, but I'd like to look at this one baseline here. So in blue here is its performance on the binary cases where you have to decide whether some rule applies or not. And that baseline is a random baseline or a majority baseline. The result would be the same. So it's essentially a random baseline, and it gets 50% of cases right. So it just flips a coin to make a decision. Since the test set is kind of small, we computed the 90% confidence interval here as an error bar. And in yellow here is the accuracy on the numerical cases where the goal is to predict the amount of tax owed. And so this baseline here just returns the same number regardless of the case. And so again, we have the 90% confidence interval here. So all of the other machine reading models perform at different levels. They all have slightly different answers. But they all perform within the 90% confidence interval of this random baseline. And so for that reason, our conclusion here is that they all perform effectively at chance level. So that is actually not necessarily very surprising, since legal language is a lot more dense than Wikipedia language. In any case, it's very different than Wikipedia language, which BERT was typically trained on. So we took this as an opportunity to build our own legal domain language models that could hopefully deal with the legal domain. So for that, one of those was LegalBERT. And so to build this, we first collected data, and we took case.law, which is a collection of all the cases that were published in the US. We pre-processed it, and we picked a subset of 900 million tokens, and we did continued language model training of BERT to get LegalBERT. To check whether this model was actually really adapted to the legal domain, we tested it on a legal term discovery task. So the goal here was to find legal terms of art in dictionary definitions. So LegalBERT was better at this than BERT. And in fact, it was also better at this than Andrew and then a colleague lawyer. Okay, so closer to the SARA dataset, we found that the perplexity of LegalBERT on the SARA cases was lower than that of BERT. So this LegalBERT was much better adapted to the legal domain than the BERT we previously used. But despite that, those domain-specific features didn't make a difference in the result. So at that point, we are sort of left with a paradox. So on the one hand, we know that machine reading has a hard time on statutory reasoning, including when you adapt them. And in fact, if you look closely at the experiments in the paper, they suggest that they're just ignoring the statutes entirely. And that's really bad because the statutes are actually the key to solving the problem. If you don't read the statutes, there's no way you can tell what's going on in the cases. So that's on the one hand. But on the other hand, based on the fact that we have a Prolog solver, we know that if we have perfect natural language understanding and if we have perfect logical reasoning, then we should be able to solve this problem. We know that BERT has really good natural language understanding, just based on its performance on other natural language understanding tasks. And there's actually evidence that it can pick up logical reasoning. So I'm basing this off a paper that was published by Peter Clark from AI2, where they show that transformers can learn to reason with rules specified in natural language. So the types of problems that we're interested in that paper look like this. So this is just a prompt that's presented to a transformer. So there are a number of facts, and then a number of rules. And then the model gets a query, and it has to determine whether the query is true or false. So effectively, what they're trying to do is train a transformer here to behave in the same way as a Prolog engine. So this works under some conditions. So this is all synthetic data, so they're able to generate as much of it as they want. And so they found that if you keep the reasoning chain, the length of the reasoning chain constant across training and test, then the model is able to generalize. As soon as the length of the reasoning chain at test time is much longer than at training time, results start to degrade very quickly. But if you stay within those constraints, if you keep the reasoning chain, the length of the reasoning chain the same between train and test, then it's actually able to generalize to any kind of domain, to rules it's never seen before, to facts it has never seen before. So from this, it looks like the main difficulty is the fact that statutory reasoning is low resource. Because presumably, if we could match the data regime, we'd be able to generalize very well. Another issue is the length of the reasoning chain. In order to do statutory reasoning, you definitely need some form of recursion. So that's still open. So talking about sizes of data sets, I wanted to contrast our data set with other data sets in legal NLP. And the first one is Quad. So Quad was built for the task of legal contract review. It's a very tedious kind of task that lawyers typically have to go through, and that involves looking closely at contracts and then highlighting those parts that are actually important. So you have to skip over the boilerplate text and then just say, oh, this clause is problematic. So they've had lawyers and law students annotate this, and they've also sent law students to a contract review class before they had them annotate. So this is the right way to annotate data, right? You use legal domain experts to do the task. So the result's a high-quality data set. But so most of these lawyers actually worked pro bono in that case, but they estimated that if they'd had to pay them for their work, the data set would have cost about $2 million. So that's a very prohibitive cost. I mean, spending an entire DARPA grant on a data set is probably a little excessive. And so the result is that most legal data sets are actually built around freely available data. So here's an example where they just scraped court proceedings that were openly accessible. Here are two other examples that were built around bar exams. So you can build question answering data sets from bar exams very easily. I mentioned that statutory reasoning was interesting beyond legal NLP, and this is one of those examples. So this is the Aristo project, which is done at AI2. And in that project, they want to build a model that can solve a science exam. And what's interesting is that the model is allowed to look at science textbooks. And science textbooks are full of facts stated in natural language and rules stated in natural language. So we kind of have the same idea, except it's in the science, natural science domain. And that project has actually been going on for 2 decades. And they've made sort of constant progress here as NLP methods have continued improving. And the last big jump in performance that they've had is actually from BERT and from BERT-like models. So it turns out that if you feed BERT with the appropriate facts, if you prompt it with the appropriate facts, it's very good at answering questions. Okay, so this paper had a number of contributions, so I'm going to summarize them here. So the first was that we built a benchmark data set for statutory reasoning. And that consisted of a closed set of statutes, a set that is self-contained for the domain of tax law, and then a number of cases that cover all of the statutes. And so these cases, this collection of cases, effectively tests a model's understanding of the entirety of those statutes. So we showed that this task was feasible by providing a Prolog-based solver, which can perfectly solve the task. As part of that, we also released corpora to train legal domain language models, and then the language models that were trained on those data sets. So we were left with kind of a contradiction between what we think transformers and BERT models should be able to do versus what they were actually able to do in practice on the statutory reasoning dataset. So this kind of begs the question, what should we do from here? So here are some possibilities. The first one is, should we invest in semantic parsing for legal text? So that would be producing Prolog code automatically from case text or from statutes. Should we try to match the same data regime as they had in the Peter Clark paper? So are there good ways to automatically do data augmentation for this problem? So either automatically, semi-automatically, anyway. Or should we go the other way around and try to make machine reading a lot more data efficient than it is? Or should we break the task down into smaller parts so that we can focus on sub-problems and then try to solve problems individually as best as possible? So in a paper that was published at ACL this year, we went mostly with the last two bullet points. So the way we presented the problem so far to a machine was, here's a paragraph of text that represents a case, and here are documents that contain rules, and now produce a binary answer that tells us whether or not a given rule applies, and tell us how much taxes are owed in that case. So that's a very monolithic way of presenting the problem. And in particular, it doesn't really tell us anything about why the model fails and which parts of the problem it actually struggles on. So it's not particularly helpful. So instead, we took inspiration from Prolog programs, and we broke the task down into 4 subtasks. So the first one, we try to identify parts in statutes that refer to the equivalent Prolog arguments. And the second task is simply performing coreference between these things that we identified. So both of these formed together, you could say, are part of a legal information extraction task. The third task is about automatically extracting the logic from statutes, the logical structure from statutes. And so that's a form of semantic parsing for the legal domain. The fourth task is done in the context of a case. And so there, you're trying to specifically figure out how the statutes align with the facts that occur in the case. So this last task you can think of as a form of machine reading or question answering for the legal domain. Okay, so I'm going to go through each task one by one. So the first one is argument identification. So here's an extract from a statute. And in that text, certain words always refer to the same thing regardless of the context. So in red here, those words always refer to the same thing. The United States always refers to the United States, at least within the scope of that task. And then in contrast, other words will take different values depending on the case you're considering. So for example, the words an employee here can refer to either Alice, or they can refer to Bob, or they can refer to anyone else who happens to be an employee in the specific case that we are considering. And in fact, if you remember how we framed each subsection as a Prolog predicate, this Prolog predicate corresponding to this specific subsection would be a predicate with a number of arguments. And so each of these blue spans here is actually a pointer to one of those arguments. It's a sort of a textual representation for one of those placeholders, for one of those arguments. Okay, so the first step was determining how difficult this task even is for a computer. Oh yeah, sorry, I should mention the task is finding those blue spans in text. So to figure out how difficult this is, we built 2 baselines, just meant as starting points. So the first baseline was built around the Stanford parser. So we just ran the Stanford parser, which is a challenge in itself on legal text, but we pretended everything worked fine. And then we picked all the noun phrases and returned those as spans. And the other baseline was built around BERT, and we framed the problem as BIO tagging. So that second baseline got an F1 score of about 60. So this shows that the task is far from being impossible, but there's still very good room for improvement. Okay. So with this first task, let's look at one subsection. And in that subsection, we now have a number of spans, and we know that they refer to certain variables. And it turns out that some of them will refer to the same thing. So the taxpayer here is mentioned twice, and then the taxable year is also mentioned twice. So that's a very typical coreference problem that you need to resolve. It turns out that legal language is very careful about disambiguating this specific type of coreference. So as long as you have all the gold spans, you can actually get really high F1 scores with rule-based systems. So we combined the first two tasks together, took the best two baselines, and the result is that we get F1 scores of like around 55. So this is a really interesting, challenging task, but which is absolutely not impossible. So it's actually, at that point, we've turned this block of text here into a predicate. And so that's predicate 2A1B. And we know that that predicate has exactly 5 arguments. And then for each argument, we know where it's represented in the text of the statutes. But it's actually not enough to consider subsections individually. Statutes and, subsections and tax law, they depend on one another. They refer to one another. And in particular, you have to know how to pass arguments from one subsection to the other. So whenever there's a reference to another subsection, it usually involves passing arguments from one subsection to the other in a specific way. So this tree, for example, is a representation of how you would possibly compute taxes. So you have to refer to lots of different subsections, and it's not obvious how to pass arguments around. So we represent those things using this prologue-like syntax with very typical logical operators. That task, it turns out, is very difficult, including for humans and including for trained humans. So instead of trying to build some form of baseline for this, we actually left this to an entire future line of research on semantic parsing for statutes. Okay. So at that point, we have a structured form of the statutes, having done the first 3 tasks. We have a structured form of statutes, and now we get a case. So a case might look like this. So there's a piece of context, and then there's a question. And so with the first 3 tasks, we've reframed section 2A1 as a predicate with a number of arguments. And so now the question is, does predicate 2A1 apply to this case, where the taxpayer argument is equal to Alice, and the taxable year argument is equal to 2017? So the question is, we haven't added any information, but it's a bit more specific. So we still expect our model to tell us whether the predicate is true or false. So we still expect a binary answer. But on top of that, we expect the model to return values for all the other arguments. So the output is a lot more structured than before, and it also adds a little bit of training signal. But definitely the problem isn't really a binary problem anymore. There are many ways that you could solve this problem. There are many types of models that you could use. You could even focus on certain subproblems. And so we simply built a baseline that's meant here as a starting point. It's just meant to gauge the difficulty of the problem. And for that, we relied on 2 things. So we relied on a machine reading model that was published by my lab mate Yunmo, who's also working with Ben. And we also used the formalism of neural modular networks. Okay. So I'll first mention that paper by Yunmo. So their goal in that paper was to do structured event extraction. So the goal is to fill out these little boxes. So this box means that if this box applies to some document, it means that there was an event where somebody died. And then that event might have an agent, a victim, and then a place, so where the event occurred, and a time when that event occurred. So this box is actually, there are many ways to fill out this box. And this is very machine readable, but not very human readable. So they decided they wanted to look at semantically bleached statements. And so you can think of them as simply an expression in language of the box. So that box you could describe as, well, someone killed someone else with something in some place at some time. What's interesting to us is that each of these these groups of words, they all point back to one of the slots in the box. And so hopefully by now you can see the analogy with statutes and the treatment we've been, and the spans we've been finding in them. So each of those spans is kind of similar to one of the arguments that we had in statutes. Okay, so the way they use these bleached statements is, let's say they found one of those events in this paragraph of text. They'll start by embedding this first span here, which represents the agent of the event. They'll feed it to BERT as a form of query. And then they'll look for a span in text, which can fill that specific slot. So let's say BERT decides that it should be US troops. So it gets added to the box here, because our goal is filling out the box. But also, importantly, they replace this placeholder with the value that they found. And so then they can move on to the second span, give it to BERT as a query, find a value, complete the box, and then replace the placeholder. And so they go through each of those placeholders in order, iteratively, until they've filled out the whole statement, and then they're done. So that's a formalism that we simply adopted for our purposes. So here, for our purposes, we treat the statutes as a bleached statement. So it's something that describes reality, but with placeholders in it, which are meant to be filled out. And then the paragraph of text is simply replaced with the case. So this is about applying this specific subsection to this case. So we first start by replacing the placeholders for the arguments for which we were given a value. So here, the taxpayer, if you can see my pointer, just becomes Alice. And then the taxable year becomes 2017. And thanks to English grammar, this remains decent. This is still understandable text. So then we move to the first argument. We use its placeholder as an embedding for a query, and then we use something that looks like squad question answering to find an answer. Then we replace the placeholder with the value that we found. We move on to the next argument, and we do this until we've found values for all the arguments. So at that point, something interesting has happened with the piece of statute below, because all of the words that were referring to variable entities, or that could refer to different things, now refer to something concrete. That doesn't change. So this thing here, you could refer to as a fully grounded statute. There are no more variable parts in it. And so now we want to figure out whether the statute is true. Well, that's equivalent to predicting whether the case would entail the fully grounded statute. So that's a simple RTE problem. We frame it as an RTE problem. And then we store the output of our model as a number between 0 and 1, which is just what's the confidence in the fact that the statute applies to the case. We have a similar mechanism for numerical values, except that we treat it as a classification problem. Okay, so this was just about applying a single subsection to a case. So figuring out whether a single subsection is true or false. But we actually have to consider the entirety of the statutes, and we have to use these dependency annotations that we built. That's actually a crucial part of the problem. And for that, we're relying on the formalism of neural modular networks. Okay, so what we do is we start with our initial query, and then we use the dependency annotations to build out a tree. And so that tree kind of represents the statutes, the structure of the statutes. You can think of the tree I had shown previously on how to compute tax. Well, that's pretty much the same tree. And each node is either another subsection with a number of arguments and values for them. So that's another query. And nodes can also be just logical operators. So we build this tree out, and we propagate all the values for arguments that we already have. We just propagate them downwards to the children. Okay, then we just traverse this tree depth first, and we resolve subsections one by one. So we resolve this one here, find values for its arguments, using the mechanism I just described before. So you keep going. Whenever there's a dependency like this, you propagate values for arguments from the child to the parent. And then when you get to illogical operators, there we have heuristics on how to aggregate information across the children. So you keep going until you get back to the root of the tree, and then you've effectively answered the query. So just to summarize, we have two nested for loops. The inner loop is at the level of a subsection, and it iterates over its arguments. So it predicts a value for the first argument, then it predicts a value for the second argument based on the first argument, and then it predicts a value for the third argument based on the first two values. So it does it's an autoregressive way of doing it. The second for loop iterates over the subsections, and it does so, it's as though you were reading the statutes top to bottom, and you would go look up references as soon as they came up. Okay, so to train this rather complex machine reading system, or rather, to train this bigger machine reading model, we used a data augmentation scheme. So in the SARA dataset, we had a number of rules, so subsections, paragraphs, sections, subparagraphs. And then for each of these, we had a case where the subsection applies and a case where it doesn't apply. So we had a pair for each subsection. But we actually translated those into Prolog. And so we have a translation for each case and for each subsection. So at that point, nothing stops us from just querying our Prolog program and asking it whether or not subsections apply to any case. So we can ask whether subsection 1a applies to any of those. So we do this for everything. And this gives us a lot more pairs of case and subsection where we know whether or not the subsection applies. So we use this, we do contrast the use of augmented data versus non-augmented data, but this helps us. Okay. The arguments in this argument instantiation task, they can have different types of values. Values can be Boolean, just Boolean values. So this is typically, does the subsection apply or not? So true or false. Some of them require an integer number, and that integer number usually represents like the amount of tax owed, or maybe the amount of taxable income. And some of them can be string values. So that's, for example, that's a string that represents a person or that represents a taxable year. We have accuracy metrics for each of them, and so we treat them somewhat separately. And in particular, our models behave very differently based on the type of answer that's expected. So we still have a constant baseline for each type of argument, which always returns the same value. So we find that on predicting the truth value for a subsection, machine reading models tend to do slightly better than the constant baseline. They do mostly worse for predicting dollar amounts. They actually tend to predict always the same number, but it's mostly wrong. And then for finding strings in text, they're actually very good. So finding string values, they tend to get the right answer. And when they don't get the right answer, they still predict something that's sensible. So they still predict a person for a person, a taxable year for a taxable year. And so when you put these three together and compute a weighted average, you find that our model, this machine reading model, which is really just a baseline, just a starting point, tends to do slightly better than the constant baseline. But what's really interesting is that, so I'm scoring it according to this argument instantiation problem, where we were interested in finding values for all kinds of arguments. But when you go back to the initial statutory reasoning problem, where you're just interested in figuring out whether a given subsection applies or not, and what is the global amount of tax owed, when you look at that, you find that our best machine reading model performs significantly better than chance level on the task of predicting whether or not a given subsection applies. So that's sort of the biggest takeaway from this entire endeavor. Additional structure that we've introduced to the problem, and then the additional data help make significant progress over the prior baseline. So those models were, again, just meant as starting points. We didn't really build very tailored, very specific models that were supposed to work very well for this problem. So I'm going to name two limitations that they have. The first one is that they don't have a dedicated numerical solver. So there was no reason that they should be particularly good at doing computations and at providing numerical answers. The other reason is that we've only made approximate use of the structure information. There was limited information flow and gradient flow between modules. And then also, so if you remember those two nested for loops that we had, we did things in a very specific order, and it was done in an autoregressive way. So answers from the future depended on answers given in the past. And that actually could be a really big problem. So there was a paper that came out of CMU, Johns Hopkins, and Facebook. It's a theoretical result. And the core of that result is that when you're doing autoregressive modeling of sequences, then that will require a number of parameters that grows super polynomially in the length of the problem. So this is just one example that they use in the paper. So this problem here is you read a SAT clause, and then you read an assignment for its variables, and then you have to predict whether the clause is satisfied or not. Well, that problem will require a super polynomial number of parameters. So it is relevant to us in the sense that when we were doing this, we were essentially reasoning in an autoregressive way. And so that will probably have inherent limitations. So this is probably not the right way to go about the problem to begin with. Another very pragmatic way of seeing this for that case is that if you make a mistake here in this box, then you just can't recover from it. It's over. You can't realize when you're here that you made a mistake here and then go back and change it. Prolog, for example, is allowed to do that. So I mentioned that semantic parsing should be its own line of research, and this is one of the reasons. So in this paper, they were trying to do semantic parsing specifically for tax law, and they picked one subsection, so 163H, and they wanted to turn this into default logic, which is like a formal representation for law. So there is no training data, so they had to rely on rules, on rule-based systems, and also they used like freely available parsers that were trained on general domain language. There was no test set either, so they just did a qualitative analysis of whatever that pipeline would output. The main conclusion was that the parser failed on most sentences. It was just unable to produce output because the language is so different. And then when it did produce output, it would actually get the scope of the logical connectors wrong. So it would fail to represent the logical structure of the sentences. So that's a particularly big problem for structure extraction, the problem we're concerned with, because that's what it's about. It's about finding the logical structure. And then the root cause for both of these modes of failure seem to be that just sentences tend to be much longer, and the parser just isn't used to them. Okay. So let me summarize the contributions of this second paper. So our goal was to subdivide statutory reasoning into subtasks so that we could focus on individual subtasks and that we could figure out where our models are struggling. So we've done this, and we've connected each of those subtasks to an existing NLP task, which has access to its own models and then also has access to resources that are in general non-legal. We've annotated the SARA datasets for each of those tasks, and then we've provided baselines, just meant starting points to gauge the difficulty for each task. With that, we're able to do finer grained diagnostics, so we can focus on subproblems. We can figure out which subproblems our models struggle with. And we also have finer grained metrics now for argument instantiation. So we know which types of arguments our model has a hard time with. So just by introducing this additional structure, these subtasks and then the annotations, we were able to get a significant improvement with respect to prior baselines. Okay, so I'm putting up this slide. You're not supposed to read it. You can if you want, but this is just other interesting things beyond legal NLP. Other interesting things beyond statutory reasoning in legal NLP. So if you're watching the video, now could be a good time to pause and just look things up. Okay. All right, so the main points here is that throughout this talk, I've argued that statutory reasoning is a really fundamental task for legal NLP. It's a task that combines natural language understanding and very rigorous logical reasoning. So we've created a data set that's meant as a very carefully crafted benchmark data set for statutory reasoning. It's made up of 3 parts. So there's a closed set of statutes for tax law that represent as much as possible the features of real tax law. We've built test cases that cover the entirety of those statutes and that test the model's understanding of the statutes. And then we've augmented that data set by adding more fine-grained annotations. And so that's subdividing the task into subparts and providing annotations for each task. So strictly beyond the legal domain, statutory reasoning is a real-world problem, which has interesting NLP features, like being a few-shot learning problem, for example. And then any advance in statutory reasoning could inform the design of models that reason with prescriptive rules that are specified in natural language. Okay, so just a few words about next steps in this thread of research. We're interested in solvers for subproblems. So in particular, we're interested in solvers for numerical reasoning. We're interested in automatically mapping statutes to the structure of the neural modular networks. So that would be a form of semantic parsing. We're interested in better legal IE. So that should help us do argument instantiation. And then most importantly, we're interested in engaging with anyone who's interested in legal NLP and anyone who's interested in any of the tasks that I talked about today. So thank you very much for listening, and I'd be happy to answer your questions.
Okay, well, that was his direct testimony. Now comes the cross-examination from the audience. I will take the privilege of asking the first question. So your LegalBERT, is that general LegalBERT or is it tax LegalBERT?
Oh, yeah, it's tax LegalBERT.
Okay, and so could you estimate the order of magnitude of effort required to create a general LegalBERT?
That has been done before, I think. That has been done, I think. I think the main effort, like the main difficulty, would be in the tax collection. So you have to make sure that you collect the text that is balanced between different parts of the law.
Mm-hmm. Okay, and the second is, when your system goes wrong, what goes wrong? And how do you diagnose that? And why can't you use that as a way of improving the system?
You mean specifically for statutory reasoning?
Yeah.
Well, I think that was the object of the second talk mostly. I think you have to probe carefully what it understands and what it doesn't. And so one reason why I wrote test cases for each rule specifically was also for that reason. So since the model has to account for sort of its reasoning path, so subsections depend on one another, you can probe at which part of the reasoning chain it has a hard time with. Does that make sense? Does that answer the question? Or?
To a degree.
Okay.
Okay, questions from the audience?
So when you annotated or converted each of your statutes and your cases to prologue, that seems like it could now become a supervised data set for semantic parsing or IE. Have you released those as annotations?
Oh, yeah. Yes, we have. So if you look at this website, it should contain all of our data sets and those things. Yeah, we've released the code, the Prolog code. And that's actually an interesting question. So it's relatively small, and it may not be, the way that I've used Prolog may not be ideal for the purposes of semantic parsing, but yes, it could definitely be used. There have been other attempts at translating parts of laws and regulations into Prolog or Prolog-like code. So some of them may still be available, but lots of them are lost because they are from the 80s and 70s.
So in the examples that you have showed, I can see that the language is towards the male-oriented pronouns. So is there any impact of this on your models, or is it introducing any biasness in models? And have you tried to integrate that?
Oh, yeah. Yes, so I should point out that those statutes that I picked for the SARA dataset, they are older statutes. In fact, I don't think any of them are. So if you try to compute your taxes with those statutes, you will be completely wrong, because most of them have been amended or repealed or changed. So in particular, yes, the way that they're written is a style that would probably not be used these days. Yeah, definitely. So in that sense, it is a synthetic data set. You wouldn't be able to take something that was trained just on this data set and then expect it to work perfectly on the rest of the of tax law statutes. But it is, I would argue, a necessary starting point, because if you now take all of tax law and try to build a system for it, you won't know where your model fails, and you're confusing lots of problems at the same time. The style being one of them.
I have another question. So near the end, what you showed is this: once one placeholder has been instantiated, it's impossible to go backwards and change the value of that. So that suggests that some kind of procedure for determining that either a contradiction has been reached or the probability of correctness is very low. That suggests maybe backtracking.
Yeah.
Is there some way of implementing that in the system?
Yes, although that is mostly meant to be future work. But yeah, I think that's definitely a necessary step. Being able to correct your conclusions is probably vital in that setting. Prolog has a native way of doing this. And I would expect any reasoning system should be able to repeal its own conclusions and change them. Yeah.
You showed that you were doing recognizing textual impairment with the grounded version of the statutes, but it seems like the only difference between that and your original baseline in the first paper is that you're grounding these statutes. Is that correct? And does that make a big difference?
It does make a difference. So yeah, first of all, you're right that that is the only difference. We've replaced variable words with the words that they actually refer to. We do expect it to make a difference because it looks a lot more. This looks a lot more. Yeah, this looks a lot more like an actual RTE problem than if you had the words be what they originally were. And then the other reason is that it does seem to make a difference here. So the gap between this here and this here is a lot larger than the gap that we had in the previous paper between the constant baseline and our machine reading models.
You talked about these kind of four tasks and that you kind of leave the third one for control. Do you anticipate challenges, if you get to the point of implementing that third one, on how these get chained together? Would you anticipate training them together? Would you anticipate finding errors in similar ways?
So I would expect that at some point we should be able to do all of these things jointly, or at least there should be no separation in between them. They're meant as probing tasks, and they're also meant perhaps to help design models by just identifying the kinds of things that they have to do. For example, tasks 3 and 4 would actually make a lot of sense to combine. So you could jointly parse the statutes into a structure and then do the argument instantiation task with that structure, and then try to optimize both jointly. The way we've written the dependencies, perhaps there are ways to take shortcuts or better ways to represent it for machine reading. Yeah.
Can you go back to the slide with the bars for the different tasks?
Which one? Sorry.
I think it was just the previous one.
Was the conclusion?
So anyway, sorry.
No. Tell me which one.
My question was just for one of the tasks for the LegalBERT, it seems that both BERT and StructureBERT aren't doing very well on that. So do you have any intuitions as to why that is?
What is it? This one?
Yes.
Yeah. Okay. So this is a good question. So it looks like it's doing a lot better. Both of these methods. So both of these bars here, they're constant, so they always return the same number regardless of the case. The way I picked this number is principled; it's not random. So it looks like for the blue bar here, it just picked a better number. But this probably happened mostly by chance. The training data is a lot larger thanks to data augmentation. So perhaps it gets the order of magnitude right, or something like that. It gets a better idea of the order of magnitude. That's possible. Also, another thing is that this test set here is relatively small. So every time you get one answer right, you gain several percentage points in precision, in accuracy. So differences can look dramatic when they are a matter of, oh, this one got 3 answers right, 3 more answers right than the previous one.
Well, if nothing further, I'd like to thank the speaker again.
Thank you very much.